You know, everything we build, from our phones to the rockets we send to space, has a physical breaking point. It's one of the biggest challenges in all of modern technology. But what if we could see those limits coming? What if we could actually design materials that just laugh at those limits and go way beyond what we ever thought was possible?
We've all been there, right? Your phone or your laptop gets super hot, it starts to slow down, and maybe it just gives up and shuts off completely. Well, this isn't just a pain, it's a fundamental barrier in physics. So what's really going on inside that chip when it starts to have a meltdown?
Okay, so think of a microchip as this perfectly organized superhighway for electricity. Everything's flowing smoothly. But as it heats up, these little rogue particles called intrinsic carriers start popping up all over the place. And they multiply like crazy, just clogging all the lanes and creating this massive electrical traffic jam. All the important, controlled signals get totally lost in the noise, and the whole system just grinds to a halt.
And this chart really shows you the hard limits of the stuff that powers our world. Germanium, which was used in some of the first transistors, basically taps out at around 100 degrees Celsius. Silicon, that's the workhorse of all modern electronics. It can't handle much more than 250 degrees. And for really high-power stuff, in aerospace or heavy industry, that's a huge problem. We clearly need something way, way better.
So this brings us to a material I bet you've heard of, graphene. It's this amazing sheet of carbon just a single atom thick, and people have called it a wonder material for years. But could it actually be the answer to this heat problem? Well, a group of scientists decided to find out in the most direct way possible, by pushing it until it broke.
To really test graphene's limits, the researchers built this incredible little setup. They took a tiny flake of it, again just one atom thick, and they hooked it up to a power source. The goal was pretty simple, just blast it with a massive current and see what happens. They were, for all intents and purposes, trying to cook it to death while watching the whole thing under a microscope.
So, how hot did it get before it finally gave up? An absolutely mind-boggling 2400 Kelvin. Now, to put that into perspective for you, that is over 2,100 degrees Celsius. That's nearly half the temperature of the surface of the sun, and it's way, way hotter than molten gold, which melts around 1340 K. And the craziest part? The graphene didn't just survive, it kept working.
Just look at these results. They're staggering. These curves shooting up show both the current and the temperature just soaring as they cranked up the voltage. A traditional material like silicon would have failed right at the very bottom of this chart. But graphene just keeps on going. Those pesky intrinsic carriers we talked about, they stay totally under control, even at these insane temperatures.
And the researchers' conclusion really says it all. A device made with graphene won't fail because the graphene itself breaks. Nope. It'll fail because the metal contacts connected to it melt, or the silicon base it's sitting on melts. Literally, everything else around it gives up first. The material itself is, for all practical purposes, indestructible under these conditions.
Okay, so graphene is incredible. Case closed, right? We found our new material. Well, not quite. Finding one wonder material by experimenting is awesome, but it's also really slow. Think about it. There are thousands of potential new materials out there. How in the world do we find the next graphene without spending decades doing painstaking trial and error in the lab?
This is the huge question that's pushing the next big leap in science. We've got this amazing success story with graphene, but what we really need is a better system. We need to go from just stumbling upon great materials to actually designing them with purpose, from the ground up. But how do you even do that?
And this is where the second part of our story comes in. Imagine if you had a sort of crystal ball that could tell you exactly how a new material would behave before you ever even tried to make it. That's the holy grail that a whole new kind of computational physics is trying to build right now.
The technical name for it is ab initio modeling. It sounds fancy, but ab initio is just Latin for from the beginning. And that is exactly what it is. Instead of looking at materials that already exist, these computer models start with nothing but the most fundamental laws of quantum mechanics. You just tell the computer which atoms you want to use, and it calculates from scratch how that new material will behave. It is pure prediction.
And the difference between the old way and this new way is just night and day. The old methods, called semi-empirical, were pretty good at explaining materials we already had, but they couldn't really predict new ones with any reliability. This new ab initio method, though, is built from the ground up purely for discovery, for finding materials with properties we haven't even dreamed of yet.
So how does this crystal ball actually work?
Well, deep down, it's tackling a ridiculously complex physics problem, simulating the trillions and trillions of interactions that happen as electrons bounce around and scatter inside a potential material. It does this by solving something called the Boltzmann transport equation from first principles. No shortcuts, no fudge factors, just the pure laws of physics. This gets rid of all the guesswork that held back the older models and creates this powerful engine to just supercharge the hunt for new materials.
Okay, so this is where our two stories, the crazy graphene experiment and the theoretical crystal ball, finally come together to create something incredibly powerful. See, they aren't two separate things. They actually feed each other.
This is the engine of modern scientific discovery. It's a loop. It starts with a real-world experiment, like the one on graphene. That gives us hard data. The theorists then take that data and use it to make their predictive models even more accurate, creating a kind of digital twin of reality. Then, those souped-up models can point the experimenters toward brand new materials that are actually worth building. And that starts the whole cycle all over again, but faster each time.
So, in the end, this isn't really a story about one amazing material or one super smart computer model. It's about creating this incredible feedback loop where experiments and theory push each other forward faster and faster. This virtuous cycle is what's going to let us innovate at a speed we've never seen before.
And that leaves us with a pretty cool final thought. We are fundamentally shifting from an age of discovering materials to an age of designing them. When you can combine real-world tests with a crystal ball that helps you predict the future, you can start to tackle the biggest challenges we face. In energy, in computing, in space exploration, the limits are no longer about what we can find, but what we can dare to imagine.